Hi, I'm Jeff Bolebruch, Senior Market Manager for Blasch Precision Ceramics, Chemical Processing Division. I want to take this opportunity to bring you up to date on a couple of significant developments in the way we've learned to design with the VectorWall. When we first fielded the VectorWall, we focused on mixing, intended to compare it to other versions of checker walls in the field. That limited us to a relatively narrow range of opportunities where there was already a checker wall of some sort, and perhaps an older burner that was less than optimal in terms of mixing. Beginning with an installation in Taiwan in 2012 that had a sour water stream and a lot of subsequent modeling and design work with our sulfuric acid technology partners, we really began to appreciate the fact that the VectorWall should not be viewed merely as a mixing checker wall, but as an important new tool for the creation of very specific environments in different parts of the furnace. In this manner, it is much more like a choke ring in that it serves as a divider between the front and rear of the furnace and provides a really unique means of secondary injection. It really is a choke ring with a twist. Blasch Precision Ceramics is active in a number of markets, mainly in areas where the application of our technology can yield significant process improvement, greatly improved component life, or improved reliability. One of these markets is hydrocarbon processing, and a number of process areas are included in the group. In sulfur, Blasch manufactures ferrules for waste heat boiler protection and VectorWall furnace internals for reaction furnaces, incinerators, and thermal oxidizers. Depending on the process licensor, there may be a number of different structures placed in the furnace to influence performance. Each has their pros and cons. Regardless of design, mechanical stability has traditionally been problematic. Initially, Blasch was tasked to develop a checker wall that would be easy to install, mechanically stable under all conditions, allow for design with varying degrees of open area, and could incorporate the use of an integral manway if desired. Concerns at this point were strictly mechanical. There were no requests for mixing or flow management. The goal was simply to put in a checker wall that could survive a campaign intact. This goal has been admirably met with no failures in service since the first non-mixing hex wall was installed more than 15 years ago. As is often the case, we became aware of this product through plant operators, many of whom were looking for a more reliable product. It was only later we learned of potential process improvement opportunities, and that eventually led us up the line to the process licensors. The blocks are designed to be stacked dry and are mechanically engaged through a series of tabs and slots, so the wall is quite stable, even when several meters in diameter. No mortar is used between the blocks, allowing the assembly to accommodate the thermally driven expansion and contraction that comes with reaction chamber operation. The blocks may also be reused. The blocks are available in a range of widths, including 230mm, 345, and 460mm to accommodate any furnace size. The walls may either be erected into a slot in the existing lining or installed against the hot face with a course of brick on either side to lock it in. The interlocking nature of the blocks makes provisions for expansion management straightforward and effective. The openings in the blocks are round, so that any portion of the block not directly supported by other blocks is in the form of an arch, and as such is in compression under load, providing greater mechanical stability than a flat span. Once the mechanical stability of the walls was demonstrated, inquiries turned to basic process questions such as, can you make it better? The result was the VectorWall, where a series of turning or vectoring inserts were developed that could be inserted into the hex wall blocks and used to create various flow fields downstream of the wall. Positive results were seen in these installations, but even more importantly, much was learned about what sorts of situations could benefit most from this technology. Situations like those with multiple feed streams requiring differing conditions at the point of entry. Rather than focus on mixing downstream of the wall by itself, a whole furnace view came into focus that drove our designers to look more closely at how the VectorWall could benefit operators in situations that required a split flow and secondary injection point. As can be seen here, a VectorWall installation may be accomplished in a very compressed period of time without the need for mortar between the blocks. At first look, this might not seem to be very relevant to a sulfur plant operations meeting, but the design and operation of these furnaces is somewhat similar, and there is some cause and effect at work here that will be relevant when I start to talk about the use of furnace internals to create specific zones. As we got more and more systems into the field, we began to suspect that the VectorWall had a more significant impact on furnace performance than just mixing. But it wasn't until this sulfuric acid plant licensor designed their new staged combustion furnace around the VectorWall that we understood the full potential for its use in situations that favor the use of a split flow configuration. This is also a good story on what can be accomplished working closely with a technology licensor to create a new furnace configuration. Again, this is more relevant to sulfuric acid than sulfur recovery, but the mechanics of utilizing multiple zones to handle dissimilar materials is important, and this is leading to a specific installation in the field and its subsequent performance. This slide basically says that NOx can be characterized as fuel NOx or thermal NOx, depending on how and where it is formed, and its formation is quite dependent on oxygen concentration, temperature, and residence time. In the spent acid regen furnace, spent sulfuric acid is sprayed into the furnace where combustion gases from natural gas-fired burners provide the heat to decompose the sulfuric acid. Fuel NOx can be formed by the combustion of air and sulfuric acid. For this reason, these furnaces typically route as much as 2/3 of the combustion air to the second zone, so the conditions in the first zone remain reducing, thus discouraging NOx formation there. The second zone must remain cool enough not to form thermal NOx when the air is introduced there. This is a Flowworks representation of a spent acid regeneration furnace that our sulfuric acid technology partner designed and built utilizing VectorWall technology for a customer in Asia. Previous to this, the standard MECS design incorporated the use of a number of offset partial walls, or baffles, to accomplish mixing in the furnace. But that approach had a number of issues, including pressure drop and a broad residence time distribution requiring longer furnaces. If the customer had NOx concerns, a staged combustion solution was implemented, and a completely separate second furnace would be used to ensure that two separate zones were created. In this case, the customer did have NOx concerns, and the retrofit with the VectorWall allowed them to proceed without the need to install the second furnace. Instead, a pair of VectorWalls were used to create two distinct zones in the same furnace, with a series of secondary air injection points located between them. In this case, we utilized a reverse choke ring, if you will, by plugging a number of the blocks directly downstream from the burners. This created the turbulence and backmixing desired to effectively decompose the spent acid. The remaining air was injected in the space between the walls and picked up by the second wall and put into rotational flow coming out of the second wall. These are a pair of screen images from some MECS modeling showing the anticipated differences between the pre-existing design and the new VectorWall configuration. These are taken at the furnace exit and depict mass fractions of O2 and SO2. This model does take into account reaction kinetics and their effects on flow. So, after all this modeling, how did we do? NOx was reduced to just 1/3 of what the train was producing before the furnace replacement. Additionally, the production rate of the train increased by 20%. The NOx reduction was attributed to substantially lower temperatures in the second zone and the increased production rate, a combination of the better mixing and tighter residence time distribution in the back half of the furnace. The example I just shared with you was slightly off the topic of sulfur recovery units, but it was the first time we have seen a VectorWall-equipped furnace purposely configured for a two-stage or two-zone operation, and the results were compelling. This, along with an earlier VectorWall installation at the CPC Taoyuan refinery in Taiwan, finally got us to thinking seriously about how we could use the VectorWall to create these specific zones in a Claus furnace in a way that perhaps avoids some of the shortcomings of the current two-zone choke ring design. This is certainly not news to anyone in the SRU business, but I wanted to include it for background purposes. It is now commonly accepted that in order to effectively destroy ammonia, the operator needs to create a region of higher temperatures near the burner and to ensure that good mixing is taking place. This design and many others utilize a structure called a choke ring to accomplish the zone separation. This is a furnace refractory detail drawing showing the approximate location of the choke ring and the secondary injection point. Again, most licensors use something similar. There is a reason for this. The choke ring is a choke ring because of the limitations of designing and building with brick shapes. The bricks need to be attached to something, and the walls are the only structure in the furnace. Therefore, most designers have determined that placing a partial restriction or ring inside the lining about halfway down the furnace would be the best way to create the two distinct zones desired and to provide the desired mixing and turbulent flow as well. With this approach, it is not possible to provide an obstruction in, say, the center of the furnace. Again, we've produced a Flowworks representation of this type of choke ring containing furnace. This is a cold flow modeling package and does not take into account the effects of temperature and reaction kinetics, but it does serve to provide a good basis for comparison of such things as velocity, pressure drop, residence time distribution, and mixing. Not necessarily absolute values, but comparative values. Some will ask, what is being missed in using a cold flow package? This data was provided by the Rensselaer Polytechnic Institute in a program looking at a number of the reactions occurring in the thermal stage and the effects of those reactions in the region immediately downstream. It is well known that the chemical reaction known as combustion leads to a rapid increase in heat and pressure in the vicinity of the reaction. What does this mean for the reaction furnace? A rapid spike in temperature just downstream of the burner and an increase in gas velocity in the downstream direction as pressure increases outward in all directions from the reaction, but only has one way to travel. So, once again, what does that say with regard to cold flow modeling? That the pressure and velocity are being underrepresented, if anything, and the effects of both on the environment between the burner and the choke ring and the flow of gas coming through the center of the choke ring are perhaps more significant than we are showing. The first thing that comes to mind when one looks at a choke ring is the reduction in furnace diameter. The above shows an increase in velocity through the center of the choke ring. Why is that? This is described by the following equation, Q equals AV, where Q is the flow in cubic feet per second, A is the area of the orifice, and V is the velocity in feet per second. This tells us that if the velocity of the gas remains constant and the area of the orifice is decreased, then the velocity must increase. This graphic was also generated by the Rensselaer Polytechnic Institute. We looked at this in terms of temperature to tube sheet in addition to velocity, and these observations seem consistent here as well. Since we are performing cold flow modeling and do not take the effects of combustion and reaction kinetics into account, this is a bit understated. Since we cannot use the cold flow model to reflect the increase in temperature due to the reaction in the combustion zone, we assign a combustion temperature for this region and follow the flow as it passes through the center of the choke ring and downstream. This is likely why some units have a second wall located directly in front of the tube sheet. These second walls increase pressure drop and can actually straighten out the flow, however. They do protect the tube sheet refractory from damage, and because of that, they are sometimes deemed necessary, despite the penalties described above. The image on the left is what the second wall often looks like. This is less than 50% open and has a substantial pressure drop impact, particularly when used in conjunction with the choke ring in the same furnace. The image on the right represents the average open area of a vector wall. There is generally only one used per Claus furnace. This image shows a two-zone split flow furnace with a choke ring in the center and a secondary injection point after the ring. Here we are looking at mixing effectiveness of the various parts of the furnace. You can see the main flow passing through the center of the choke ring, and the secondary flow, which is offset from the center line, wrapping around the main flow and is not immediately integrated into it. This matters because you have half the furnace remaining to combust 2/3 of the acid gas. It is important to note that in order to start calculating residence time, you need to start counting from the time that the two gases are actually in direct communication with one another. The sooner you can get them well mixed after the secondary stream is introduced, the greater the chance of getting full reaction prior to exiting the furnace. This is a histogram showing the residence time distribution of this furnace. There are two peaks because of the way the gas acts in relation to the choke ring. Some of the flow goes straight through the ring as described earlier, and some is rejected. This mechanism creates two major distributions, and the overall residence time distribution is quite broad, meaning there is a risk that the gas that flows unimpeded through the choke ring may not be fully reacted, particularly with the secondary flow. The relative size and velocities of the main versus secondary flows may make it difficult for the two to mix as quickly as desired. The time axis of this chart may not be accounting perfect, as the cold flow model assumes away a lot of the reaction kinetics, but it is enlightening to compare it to the histogram in the VectorWall case. This, on the other hand, is a Flowworks representation of a VectorWall in the same location as the choke ring. The blocks around the periphery are plugged, as though this were a choke ring, but instead of an open center, there are vector tiles, which force the gas to rotate at this point as it passes through the center of the wall. This does a number of things. It sets up a rotation and subsequently a plug flow configuration downstream of the wall, ensuring a very tight residence time distribution, making more efficient use of the furnace volume, and potentially increasing capacity. It also ensures that the secondary stream is more completely mixed earlier and also homogenizes the flow at the tube sheet, greatly reducing the likelihood of hot spots at the refractory face and eliminating the need for the second wall we discussed earlier. In the VectorWall equipped furnace, we can see clearly that the radiant component of heat is being reflected back from the structure of the VectorWall as well as off the vector tiles inserted in the holes. This ensures that more heat is retained on the upstream side of the VectorWall and the potential for a long, high-temperature plume reaching the tube sheet is eliminated. This profile was run with the current VectorWall design, which shields 50% of the opening from direct line of sight. In this view, we see a VectorWall substituted in the same location the choke ring was previously. The main difference is the nature of the flow through the wall. The gases come out rotating, and in so doing they incorporate the secondary stream into the flow early on and move forward on a relatively even front, with a long path length but a tight distribution. The histogram for the VectorWall shows a single narrow peak. Ideally, this is centered on the optimal residence time, but that would be determined by the furnace length and location of the wall within the furnace. We have modeled the VectorWall in the same location as the choke ring, but we believe, based on field experience and the mechanical reliability of the design, that the VectorWall could and should be located a bit closer to the burner than that. We are working with Rensselaer Polytechnic Institute and their chemistry department to develop a more quantitative means for determining the exact location. We know that the temperature in the zone of combustion rises rapidly and falls off. That would likely be the optimal location for the VectorWall. This is an update of what turned out to be our first TwoZone split flow installation at the CPC Taoyuan refinery in Taiwan back in early 2012. There is a significant increase in the difference in temperature between the upstream and downstream sides of the wall. In fact, this furnace had suffered from random hotspots on the shell before the installation and had painted the steel shell with a temperature-sensitive paint. There's currently no missing the location of the wall in the furnace, even from 50 meters away. The furnace is a different color on either side. Also, this furnace had a significant vibration problem prior to the installation. That went away completely. As the temperature in the first zone is now higher, the amount of ammonia-bearing gas that can be processed in the same space goes up, in this case nearly 50% more. The red line shows the sour water stripper gas, and the blue is the acid gas. So far, we have focused on the creation of the two distinct furnace zones. The first, a hotter, higher pressure reaction zone, or zone of mixing, and the second, a lower temperature zone dominated by the reassertion of order, or zone of flow. We have not previously looked at fine-tuning any of the other aspects of the vector wall. We have looked at a number of vector wall tile profiles and more or less stayed with the first one we tooled. It has proven to be a good combination of mixing and low pressure drop. We have fielded a more aggressive mixing profile, but at a pressure drop penalty. Recently, however, as we've begun to view this as a choke ring with a rotational center and a heat reflective capacity, we've revisited the vector tile design yet again. For those earlier, more aggressive mixing designs, it turns out that the increased pressure drop was coming from the compression of the flow through the smaller openings in the vector tiles. We found that if we continued the spherical profile further out until it extends past the entire opening, but does not decrease the cross-sectional area of the hole in the block as we are turning it, the pressure drop does not rise appreciably. This design has not yet been fielded, but is ready for commercial use. Once we started to model two-stage furnaces with a relatively few points of secondary injection, we found ourselves trying to work around a combination of suboptimal locations and relative weak flow strengths. Someone then asked, what if you could inject a secondary stream into the furnace from across the entire backside of the vector wall itself? Fair question. When we went to the larger blocks, we decided to control weight by removing material in a series of bands around the blocks. We had no idea at that time what the implication of that would be. As you can see from these photos, the bands of removed material all communicate with one another, forming in effect what is a series of plenums within the wall, from top to bottom. As you can see in this cutaway, there is substantial interstitial space in these walls. The first question was, what to do with it? We believed that if we could introduce a secondary stream into that plenum space and then cut the corners of the blocks on the downstream side, there would be an avenue for the gas inside the wall to escape. Or more accurately, hundreds of avenues for gas to escape. This modification has no negative structural impact on the wall itself. We modeled a series of hole sizes and injection pressures in an effort to optimize the effect. Here's a video of a vector wall, or injector wall, with a series of 15 mm average diameter exit holes. It did not appear that we were going to create a lot of pressure drop trying to force the secondary stream into the wall. In fact, if anything, we were going to have trouble filling the entire wall in a way that would create an even distribution from top to bottom. Perhaps we can work with variable hole size if needed, but then again, even if only the upper half of the wall is injecting the bulk of the secondary flow into the second zone, we are still talking about hundreds of injection points on a large furnace. We've come to view the method of secondary injection in terms of the flow of water. The existing single point of injection can be compared to a tap pouring water or colored dye into a bath, whereas the injector wall can be seen more as a shower head spraying the same fluid from hundreds of nozzles. This is a Flowworks close-up of the secondary flow exiting the injector wall holes and being caught up immediately in the flow exiting the vector tiles all about them, virtually instantaneous mixing into the bulk stream. The integration of the secondary flow into the main flow is so quick and so complete it is barely visible here. Thank you for listening to this presentation. If you have any questions, please feel free to give me a call.